Hello, this short talk will be about the size of the simulated system and also on the necessary time. The size of our simulation cell depends on several circumstances. First, there are physical circumstances, particularly this is the correlation length. The correlation length is a distance after which the parts of the system do not know about each other, or they are not correlated. You already know the concept of the radial distribution function. So here there are strong correlations over the distance, let us say to about 1 nanometer, but after 2 nanometers or 3 nanometers this curve is flat. It means that there are no correlations. Of course, our simulation box must be bigger than this correlation length. This is the minimum we need. But there are also technical aspects. This is the range of the potential. In principle, the Lennard-Jones potential has an infinite range. Of course, the potential is very small after certain distance, and we need to do tricks how to treat this. Similarly, the simulation time depends on the correlation time. That is the time after which our configuration doesn't depend almost on the configuration in some older time. This is the property of the system, and of course it's measured in nanoseconds, picoseconds, and so on. These are short physical times. But then we have certain code, it has certain efficiency and also a time step. And for example, such 10 picosecond system will be calculated, let us say, in 1 hour. This is called a wall time. Often we are using parallelized codes, then wall time includes several threads, several CPU units or GPU units which work in parallel. Typical liquids, simple liquids, require at least hundreds of molecules to give reasonable results, and times, let us say, on the order of picoseconds. However, more complex liquids like ionic liquids with bulky cations and anions, these are also viscous. They need longer times, at least nanoseconds, tenths nanoseconds, and so on. Huge systems and also long times are needed in biochemistry. Such biochemical systems need, well, up to 10,000 up to millions of particles. To calculate structure we need nanoseconds. For complex phenomena like binding of ligands and stuff like this, we need microseconds. And top simulations that try to simulate protein folding and similar phenomena are able to reach millisecond scale. For different nanostructures, crystal defects, and such stuff, we may need billions of particles, for example, for these crystals, but the simulation times may be very roughly nanoseconds. Of course, there is a principal problem here. The larger system, the longer the correlation time. So to simulate large system means to simulate for a longer time, and the wall time then will be longer because of both aspects. We need more calculations to simulate a larger system, and also we need to simulate it for a longer time. You know what is a pair potential. This is the simplest example, and the question is how many calculations or elementary operations do I need to proceed by one step in molecular dynamics, or one cycle, that is one attempted move of every particle in Monte Carlo. If I use the simplest algorithm, then I will use a double loop. So I will check every pair of particles in periodic boundary conditions, let us say the nearest image, and there are roughly n squared of them. It means that a double system would be simulated, or the wall time would be 4 times longer. It's not good. But if I use a sufficiently short-range potential, then the optimum algorithm will require only n operations. So it's a better so-called scaling. We shall see that with electric forces this is not so ideal, but still it is not so bad. Okay, so let's return to the simplest case, to the Lennard-Jones potential, for example, atom-atom potential. I have said that it's necessary to cut it off, to shorten. The simplest way how to do it is to use the simulated potential equal to the correct one for distances shorter than certain cutoff. Typically this cutoff will be less than half the box size, and I ignore it for longer distances. However, in molecular dynamics this would correspond to a jump. So it's not good for molecular dynamics, because a jump in a potential means an infinite force. One possibility how to avoid this is to shift the potential after cutting. That is, I subtract its value at the cutoff. It's even better to smooth the potential, to cut it and smooth. Here is an example how to do it with enlarged one, and I will show it on a graph. This is the Lennard-Jones potential going up to about 1 nanometer, and if I enlarge it, it's seen that this yellow is the original one. It was cut at 1 nanometer, but it was smoothed from here. Actually, it was cut somewhere here and it was smoothed. And these are the forces, the corresponding forces, which is the derivative of this potential. Here we can see that forces, the cut forces look like this. That's because that these forces are a derivative of the potential before. This is just one possibility how to do it. There are many possibilities how to do it. Okay, so we would like to cut the potential, to shorten it. It's a good idea to estimate the error we do in this way, the systematic error, or the correction. As a simplest case, let's calculate the correction of energy. This correction of energy will be the integral from the cutoff to infinity. I am using here the simplest case of the potential, which is just cut. This case can be treated in the same way, it's just a bit more complicated. And I will assume that the cutoff is long enough so that the liquid or the system beyond this cutoff is not structured, that the radial distribution function is unity. Then the estimate of this energy correction is this integral. The pair potential is a function of distance. This is the element of integration of volume of a shell around the center, and this is the number density. Okay. The dispersion forces, the main part, the main attractive part of the Lennard-Jones potential, behave like the distance to -6. It looks fine. I have the integral that contains I will not write the constant here, r to minus 6, and the element is r squared. Here it is here, times the r. Is the integral over r to minus 4, and it does converge. And the result is that this correction is proportional to the cutoff to minus 3. Okay, doesn't look bad. Typical values which are used are nowadays several Lennard-Jones sigmas. In old times 2.5 used to be used. It's considered now too imprecise. Typically for typical atoms it is from 8 to, let us say, 15 angstrom. But okay, we have also Coulomb forces. So let's try to put here the Coulomb force 1 over r. But apparently such an integral from cutoff to infinity doesn't converge. So we are not able in a reasonable way to cut the Coulomb potential at all, because we are not able to calculate the correction. There's something wrong with it. Actually, the limit of this is already from the dipole-dipole term. If we put r to minus 3 here, we'll get the integral over r to minus 1, and it doesn't converge. But the dipole-dipole interaction depends on the angle, so this is not so bad. But for charge, it is bad. So what to do with the Coulomb forces? We cannot calculate, or we can, I will show it later, but it seems that would be a very difficult problem to include very many interactions with very long distance. Okay, still it is possible under certain circumstances to use cut and shift potential also for the Coulomb forces which behave as r to minus 1, better said Coulomb energy forces r to minus 2. But it must be done very smoothly. It is very cheap method, but quite inaccurate. But the computer time scales the number of charges in the system. It is going to work if my system is, for example, a molten salt, and its cutoff is much longer than the so-called Debye screening length. You probably have heard about this concept when in the physical chemistry you know there is a Debye-Hückel theory. So it's part of this business. The typical Debye screening length, for example, in 0.1 mole solution of sodium chloride is about 1 nanometer. But this is considered as inaccurate. There is a better method. This is called the Ewald summation. I will speak about it later in some small detail, I would say. But there's no free lunch. For the standard Ewald method, as I will write shortly, the computer time scales n to 3/2. It is in between the pairwise method, which would have n squared, and good limit of about n. But this method can be transformed into something that is even more complicated, and then the computer time scales almost as n. The logarithm actually isn't so large, but there is a big number in front of it. There are other methods, but they are not suitable for simulations, although they are used in astronomy, because as you know, in astronomy we have the potential of the same behavior. But in astronomy we have masses, and all charges are positive and they attract each other. For dipolar systems, we have another method possible, that is for systems which do not contain free charges. It is a so-called reaction field method. And this method is based on a cutoff and a smart way how to calculate the response of a dipole here from the surrounding liquid, which is treated as a dielectric continuum. So a few words about summation. We'll do a smart trick. We'll take a periodic system as here, and we will calculate in principle the interaction of all charges in all these images. It looks like nonsense. It means that we have many more interactions to calculate, an infinite sum over all periodic images, and to calculate this pairwise additive interaction, 1 over the distance between these particles, over all pairs. But there are very fine mathematical tricks how to simplify this huge double, or actually not the double, this huge sum actually. The trick is following. Instead of using point charges, I will take a Gaussian charge distribution around, so that it cancels out the point charge, so that every point charge will be screened by such a Gaussian charge or smooth Gaussian charge distribution of opposite sign. These screened charges are short range. It means that such a sum will converge very fast. But of course, I must fix it because I added some extra charges. But these extra charges are smooth, and they can be summed up in the K-space, in the reciprocal space that is like waves. If you don't understand it in detail, doesn't matter. Okay, here is the mathematics. Here is the final formula. Of course, you don't have to memorize it. Instead of one huge sum, I have here two terms, and both sums are fast converging. This is important. So I can use only a couple of terms. The first term has the same structure as the normal pairwise additive term. No principal problem with it. The second term is something that may remind you the Fourier transform or Fourier series. And here comes a trick. Instead of calculating this directly, I can use certain smart tricks how to improve the efficiency, to use the so-called fast Fourier transform. Perhaps you have heard about this approach in some other subjects, but if this is done, it's not easy, but no details for this course, then I'll get a method that can calculate all interactions in a periodic system between n charges within computed time, which is proportional to n times a logarithm of n. There's quite a big constant in front of it, but for large system it does pay. Thank you for your attention.